Remember last time we were working on inverses, how to find inverses and what we can do with inverses in terms of solving equations. That's going to be very advantageous once again for you guys on this material. But again, we're getting through the material, so the next type of concept we're going to do here is, again, solving systems of equations, but we're going to do it in a very special way called LU decomposition or LU factorization, depending on which textbook you use and stuff. So this is section 2.5. That's what I got up to last time, but I didn't get started on 2.5. So today I'm going to do 2.5 and then move on to section 2.6. But if you think about your homework set that I set up for you, the online one and the one on our Canvas page, that homework set honestly is from 2.1 through 2.5. So this first part, 2.5, is on that homework set, that quote-unquote LU decomposition, LU factorization stuff. So let's get started on that, and let's talk about the reasonings behind it. So here it is, LU factorization of a matrix. So here's the idea, the theory behind this. So we have an equation, the old famous equation we've been solving for. AX equals B. You want to solve for X. X is your unknown here. So typically what we do is we have to find A inverse and then multiply, on this case, on the left side, A inverse on both sides, and X will be equal to A inverse times B. Well, it really depends on the size of what A is and finding its inverse. So if you could factor it. Now, this LU decomposition, LU factorization, is a very special thing. What we want here is to basically factor, which means as a product, of L times U, okay? And we don't, these letters are not just randomly picked out of space because I like L's and U's. L is lower triangular and U is upper triangular. So we're going to factor this matrix A into a lower triangular, upper triangular. Now the lower triangular has a special look, okay? It's going to be, the L is going to be, you know, n by n, it's going to be a square matrix here. You get ones on the diagonal, and off the diagonal, below it, you're going to get some numbers down there, but above, it's called a lower. Lower triangular, you got numbers lower than 1, but above, you're going to have a bunch of zeros. So this is my L for my lower triangular. You get numbers in the lower spot, but in the upper spot off the diagonal, you get a bunch of zeros. And then you got U. Now, I never said A had to be square on this thing. So if A is not square, A inverse doesn't exist. But I still want to solve for X. Is there a way I can do this? Well, in the old days, when it wasn't square, we would take A and augment with B and do row reduction on that thing and get RREF, and then be able to solve for A, X, and write it in terms of you know, the parametric vector form of an equation, of your solutions there, parametric vector form. So here's the deal. LU. L is lower triangular. Ones on the diagonal and numbers below those ones is going to be numbers. Some of them will be zeros, some of them won't be. But the upper part is going to be all zeros. And then your U factorization is what we call upper triangular, so you can get numbers. You could get some zeros on the diagonal, main diagonal. It does not have to be square, may not be square, but the upper part, you're going to get a bunch of numbers. So LU factorization. So we're going to break it apart where there's an L matrix that's square and a U matrix that may not be square. It would be whatever the size of A is. So let's say, for example, A is M by N. This is going to be M by M. This one is going to be M by N. This size matrix will be the same as what matrix A is going to be in terms of size-wise. But this is what it's going to look like. Now, ones on diagonals. You've got to have your pivots. They're all got to be ones on the diagonal to be able to find the solution. For the lower. For the upper, you're not going to get ones. This is going to be basically in REF. You get number, and then you get your pivots here, and then they don't have to be ones, but then it's going to be above that is going to be numbers that are not zero. Below the diagonal are going to be zeros. Okay? Why in the world do we want to do this factorization? First off, if A inverse exists, and we're saying it may not because A is not even square. If A is not square, A inverse doesn't exist. You got to have a square matrix. But even then, you got A times X equals B, and using A inverse, if you're going to find A inverse, it's going to take 2 to the n cubed operations to be able to do this. 2 to the n operation. I'm sorry, 2 times n cubed operations to do this. You know, that A, get a pivot here, sweep down, next one get a pivot, sweep down, sweep down, sweep down, and then sweep back up. It takes 2 n cubed operations to do that. Again, remember, n may be large. So, now if we solve this thing using the LU factorization on this, replace A with LU, it's only going to take 2/3 n cubed operations. Okay? So it divides the time by 3 is what's really going on here. Does that make sense? Now, you guys that are computer science majors and computer engineers out there, we're talking about, you know, how long does it take the operations for the computer software or whatever to go through its routine to be able to find the solution. I can cut the time down by 1/3 is what this LU factorization is doing for me. Does that make sense? So that is why you want to do it. Now, yes, if A is something small, like a 2x2, a 3x3, you know, then you're going to go, I don't think this is even worth it. And you may be right, that it may be even fast just to find A inverse than to go through all this decompositioning things here. But if we're talking about 4x4, 5x5, 10x10, 120x35, they don't have to be square. I mean, it takes a lot of processing to be able to do that. And by doing an LU factorization, you can cut down your time by 1/3. So this is more for my programmers and my computer science majors and engineers out here and stuff. So this is the idea of taking a matrix A and doing something called an LU factorization on this guy. Now, how do you solve this AX equals B type thing here? Well, let me show you. Here is the idea on how to solve. So what's going on? You've got an equation, AX equals B. And if you can rewrite A as L times U, lower times upper, okay? So instead of AX equals B, you're going to have LU times X equals B. Okay? Matrix L times matrix U times the X vector equals B. Well, I'm going to do associativity on this thing, and I'm going to move my parentheses around. That's the same thing as having L times UX equals B. Okay? Now, we're going to do a little substitution here. So I got LU times X equals B. My goal here, at the end of the day, is to solve for X. So I can rewrite that as L times UX equals B. Now, note, you're going to let Y equal to UX. So you're going to break this into 2 parts. So you've got L times UX equals B. Replace UX with Y. That's going to give you L times Y equals B. And you got this other equation. Now you've got a system of equations. You've got UX equals Y, U times X equals Y, and LY equals B. Okay? So, you are going to be given B. You are going to either have to find or you're going to be given the LU. Your goal here is to solve for X. So you're going to do this in order. Once I replace YX and set that, UX and set that equal to Y, so you end up getting LY equals B, you can solve for Y on this thing. How would you solve for Y? So 1. First, solve for LY equals B, solve this thing for Y. You can use, let's say, this thing is not square or whatever, then I can do L augment with B, do my row reduction on this thing, and be able to get my solution for Y. And once you get Y, then you go back to this, UX equals Y, and I do the same thing, put U, augment with Y, do my row reduction, then I can solve for X, the solution. So to give you guys a general equation of what's going on here in this process, this algorithm, it is this. Here's X, here's B, and these are the world where they live at. I multiply A times X is equal to B. So that's your straight line shot. But I'm creating this third world over here where I take A, I take X, multiply it by U, that's going to give me Y. Then I'm going to take Y, multiply it by L, and that'll give me B. So we're giving it a 2-step process. But the nice thing about this 2-step process is you got lower triangular and upper triangular, so you've got half the work already done. So solving for the eventual X on this guy will actually take less time to do it. Less CPU time, less computer time, less running the algorithms through the software system or whatever the case may be. So this is the idea right here of trying to create a faster way of doing this problem. So This is linear algebra. I talk about theory, but the next thing I'm going to have to do is actually show you guys an example on this guy. So, again, I'm going to give you guys an AX equals B, and in this first one, I'm going to go ahead and give you what the LU decomposition is, what the factorization is, and I want you to solve this equation. So, turn my page over. Here it is. So, of course, I went a little bit beyond 3 by 3 because this process, I don't think it's worth it if you do 2 by 2s or 3 by 3s. But once you start getting to 4 by 4s and 5 by 5s and 27 by 32s and all this other one, you begin to appreciate this technique because it does save you some time. All right. As long as you've got that LU factorization here. So, here we go. I'm giving you matrix A. Matrix A is negative 1, 2, 4, 1, negative 4, 15, 13, 6, 1, 12, negative 8, 2, negative 3, negative 29, 31, negative 6. I went ahead and did the factorization for you. So the L part, which is your lower triangular, is going to be squared. This thing's 4 by 4, so you get 1s on the diagonal. And below the diagonal, it is 1, 4, below it if you look column-wise, a 1, 4, negative 1, 3 on the column. Then it's 0, 1, 2, negative 5. Then it's 0, 0, 1, 2, and then it's 0, 0, 0, 1. Okay? And you'll notice right here, one's got to be a pivot. So you're doing it to the column. So all I did was really just change the signs of this guy, put that guy in there. But then there was some more operations to be able to do to get the L out of this guy. We'll talk about how to get that later. But this is my L, lower triangular. The numbers are in the lower part off the diagonal. The U part is going to be this guy. And I'll just read this row-wise. Negative 1, 2, 4, 1, 0, 7, negative 3, 2. Okay? 0, 0, 2, negative 1, and 0, 0, 0, 0, 0, 0, 3. This one is upper triangular. But notice you do not have 1s for pivots. You've got the pivot positions here, but then above the diagonal, you got non-zero numbers in there. I mean, you could have a 0 there, it wouldn't matter. But you just have numbers up here. The lower part of your U is all going to be zeros, and that's what I got. So this is upper triangular, this is lower triangular in terms of our definition of upper and lower triangular. Okay? Now, first thing you need to do is this. If somebody's giving you something or other, you should always check it. And that means you. If you're going to create these guys, you should go back and check yourself. Because how many times have I seen people do the LU decomposition and they screwed up something with L, so their L times their U does not equal the A originally got. So you won't actually get the right answer. So the first thing you should do is verify that A is equal to LU. You take L, multiply by U, row by column. Negative 1 times a bunch of zeros. 1 times 1 with a bunch of zeros, negative 1 with a bunch of zeros. That's going to be 1 times negative 1 gives you negative 1. First row, second column. Okay, you get 2. You notice it's the same thing all the way across. Negative 1, 2, 4, 1. And then second row, first column, negative 4 times 1 is negative 4. And then second row, second column. 4 times 2 is 8. 1 times 7 is 7. 8 plus 7 is 15. So, and you can do the rest of it. I verified this for you. I multiply L times U, and I do get A back again. I did right. Okay? Now, I want you to solve this equation. AX equals B, where B is equal to this vector. 9, 35, negative 6, 39. I want you to solve for X. AX equals B. Here's A times what X, X1, X2, X3, X4, would be equal to this B. 9, 35, negative 6, 39. Okay? So, here we go. Since I have my LU factorization, step number 1 is to do this. As AX equals B, you know what a double arrow is, if and only if? L times U times X is equal to B. I replace A with L times U. Okay? Well, the L times UX equals B. And I'm going to let times X equal to Y. That guy right there. I'm going to set him equal to Y. So, I'll get L times Y vector and I'm gonna just, this is part one right here, step one, I let y equal to ux, so this would give me L times y equals b, and then I'm gonna go and solve for y. All right, what was L? L was up here, 1, 0, 0, 0, 4, 1, 0, 0, negative 1, 2, 1, 0, 3, negative 5, 2, 1. There's your L times y. The y vector is going to be y1, y2, y3, y4 is equal to the b vector, which they gave that to me as 9, 35, negative 6, 39. So here's my L times y is equal to b. I got a question for you. How would you solve for y on this thing? Knowing what you know about linear algebra, I got this L matrix times y matrix equals the b vector, okay? How would you solve for y? What would you do? Augment. So augment, this would be 1, 0, 0, 0, augment with b, which is 9, 4, 1, 0, 0, that would be equal to 35, negative 1, 2, 1, 0, that's equal to negative 6, okay. And then the last one is 3, negative 5, 2, 1, that's equal to 39. Okay? I augmented as you recommended. Now, how would you solve this thing? What you going to do? You're right. You're going to take the 1 and sweep down. You're going to take this 1 and sweep down, take this 1 and sweep down, and then you've got it. Does that make sense? So basically, for this one, because I got 1s on the main diagonal, it will not be very much difficulty for me to do this. RREF. I'm just going to save myself some time. You take that 1, multiply first row by negative 4, add it second row. Take the first row, add it to the third row, and take negative 3 times the first row and add it to the third row. Then you sweep down here, and then sweep down here, and then you got it. Does that make sense? So you can go RREF on this guy, and you're going to get 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Because you notice you have pivots all on the diagonal. This L is actually square. And it's augmented, so I can put my little augment thing here, times, these numbers is what you get. You got 9, negative 1, 5, negative 3. Okay? This tells me, right here, by doing RREF on this guy, and I did skip some steps on this, this tells me that the y vector is actually equal to 9, negative 1, 5, negative 3. Notice it is going to be a unique solution. But I knew it was going to be a unique solution because in my LU factorization here, you've got, it's going to be a square and you've got 1s there. You've got 1s for pivots already. So it's not real difficult to sweep down and make the rest of them zeros. And that's what we've done here. And that gave me my y vector. That's step 1. Once you get the y vector, you go into step 2. Okay? So for step 2, now you're going to do this ux equals y. How would you solve this? Well, this actually means that u was this vector, this matrix right here. I'm just going to recopy them. It is negative 1, 2, 4, 1, 0, 7, negative 3, 2, 0, 0, 2, negative 1, and 0, 0, 0, 3, times x vector. So your x vector is going to be x1, x2, x3, x4, and you're going to set that equal to the y vector, which we just solved for, which is 9, negative 1, 5, negative 3. Question for you. How would you solve this guy? Solve for x. Solve for x. What are you going to do? Well, augment the matrix again. So we're going to augment. This is going to give me negative 1, 2, 4, 1, augment 2, augment with -1. 0, 0, 2, -1, augment with 5. And last one is 0, 0, 0, 3, augment with -3. Now, solving this guy, what are you going to do now? When I have the L, and L times Y equals B, I swept down for the L. Now that I have, and to be able to solve for Y, now that I have the Y, what am I going to do with the L augmented with Y? What am I going to do? Sweep up. So I'm going to sweep up and make zeros in here and here, and then take this guy, sweep up, make this guy sweep up. I would make these guys pivots as well, 1, so yes, you may end up getting some fractions here, but I don't think so. And so, again, I'm going to just shorten my little notation here because I'm just talking about the theory behind this thing. I'm going to once again go RREF on this guy, and because these are all numbers on the diagonal, they're all going to turn into pivots. 1, 1, 1, 1. These are zeros above and zeros below, and it would be augmented with 0, 1, 2, -1. And that ends up giving me what the x vector is. What's x going to be equal to? 0, 1, 2, -1. So in the form of ax equals b, x is actually equal to the vector 0, 1, 2, -1. There's my answer. And I know you're looking at this stuff going, why would you ever want to do this? Again, the trick is this: large systems of equations. Now, we haven't done really large ones. I mean, I threw some on your test, which were like 5 by 6s or something like that. Now, I'm talking maybe even worse than that, 10 by 12s or 15 by 37s or something like that. It takes just a while just to start row reducing this stuff. But, as I mentioned before, why you want to do this is this right here. If I solved it the original way, trying to use A inverse and be able to augment A with the identity and do my row reduction, it's going to take 2 n cubed operations to do that. But by doing the LU factorization way, it cuts it down by 1/3 of the time that it takes, or the steps it takes. So it's 2/3 times n cubed operations. So it saves time, especially when the matrices are actually quite large. Okay? So, that is the point of the exercise. So, with that being said, big deal here. So, hopefully, look at this example of exactly what I did, because this is your algorithm right here of how to solve this thing. If you've got, up here we got A, and we can get that LU factorization. So, I got AX equals B, where I'm going to give you some kind of a B there, and I gave you A. If you can do an LU factorization and replace A with LU, LU times X equals B, you basically do U times X, call that part Y, so you end up getting UX equals Y and LY equals B, and then you start on the outside, LY equals B, and you solve for Y, and again, because it's lower triangular, it's going to be half the time, because you already got your zeros above it, and then down here, you've got, once you get Y, you put UX equal to Y, you got your U, augment with the Y to be able to solve for X, and then all you got to do is sweep up and put ones on the diagonal, and that again takes you a lot less time than you got the answer. So it's a time-saving device. Question?
If we were doing this on the test, would we have to show work
Don't know. I haven't decided yet. He made it to test. So, part of it, if it's small, I'll make you do it by hand. If it's large, I'll let you use the calculator on it. That's pretty much what I'm going to do here. But it's an excellent question. How much can I actually do on the calculator? Because, yes, okay, I'm cheating on this thing. I went ahead and do RREF, but I'm trying to show you the operations. But it should not be difficult to do this by hand because you already got it already lowered. So all you got to do is sweep up to make this guy and make pivots, of course. Okay? But the hard part is this part here, finding L and U. So with this, you're probably right. I'll probably let you use the calculator to be able to go from L augment with y and be able to solve, augment with b and be able to solve for y, and then take your u, augment with y, and be able to solve for x. I may let you use the calculator to do that, because you guys are experts at this, otherwise it's probably gonna take you so long. Where's the hard part gonna come in at? How do you actually do this LU factorization? That's where the real gist is, and that's what you gotta show me to work on, okay? So, let's do one. Because I can show you, I can talk about theory behind this stuff, but the reality is, until you actually do it, well, it takes some work to be able to do this thing. Now, here's the real deal. Since you're bringing up test questions, which is an excellent question, no arguments there, this is what I plan on doing. I'm not gonna make you do one problem, where here's A, and set it times x equal to b and make you solve for x on this thing. Because here, and I'm going to tell you, use UL factorization to be able to do this. Because if you screw up the UL factorization, what are the odds of you getting the right answer for x? 0 probability. So what I'll do is I kind of do it in two problems. Like the last problem, I will give you A, and I'll give you what its factorization is, and then tell you, show me the steps and what you do, and even then I will let you use the calculator a little bit on that. Be able to solve for x, but you have to show me what you wrote down, what the work is in terms of getting that, okay? And then on the next problem, I'm going to say, hey, here's a matrix, do the LU factorization. So it's not all in one big problem. I'm kind of putting it in two small problems. So if you do make a bonehead careless error, it won't completely blow you out of the water in terms of point totals because you messed up part A. You're never going to get part C, D, and E on this thing. Does that make sense? So I will break it up because I'm trying to be fair that if you make a bonehead careless error, well, I don't want you to lose a bunch of points on it. You'll lose points on not getting it right, but it won't affect all the other problems on the page. So, here's the deal. U is that upper triangular, and L is that lower triangular type thing here. So, I got a matrix here. First off, identify the size of this matrix. So, we want to do the LU factorization. A is the matrix 2, 4, negative 1, 5, negative 2, negative 4, negative 5, 3, negative 8, 1. 2, negative 5, negative 4, 1, 8, and negative 6, 0, 7, negative 3, 1. What size matrix is this sucker? It is 4 by 5. Notice, it's not square, okay? But I want you to do the LU factorization. So, U is for upper triangular, okay? L is for that lower triangular, all right? And these are where your pivot, where your numbers are going to be at. And you kind of do it at the same time. Let me show you, demonstrate for you. All right. So this is basically going to find you. Let's start with A and write it down. A is the matrix 2, 4, negative 1, 5, negative 2, negative 4, negative 5, 3, negative 8, 1. 2, negative 5, negative 4, 1, 8, negative 6, 0, 7, negative 3, 1. There's A. We're going to make this thing upper triangular, okay? Upper triangular means we're going to have zeros below it. So how do I do zeros or below it? I'm going to take that 2, and I'm going to sweep down and kill the negative 4 off. I'm going to sweep down and kill that 2 off, and I'm going to sweep down and kill that negative 6 off. How do I go about doing that? I'm going to take 2 times row 1 added to row 2. Remember, I'm going to shorthand this thing because I'm going to run a room writing this stuff out. Whatever row I add it to is the row I replace. Now for the next one, I'm going to do negative 1 times row 1 added to row 3. And then for the third one, I got a 2 I want to kill off a negative 6. I'm going to multiply it by 3. 3 times row 1 added to row 4. And whatever row I add to is what I get. And what do I get when I do that? Okay? Here we go. The top row stays the same. 2, 4, negative 1, 5, negative 2. Well, 2 times 2 is 4, plus negative 4 is 0. That was the point. 2 times 4 is 8, plus negative 5 is 3. 2 times negative 1 is negative 2, plus 3 is 1. 2 times 5 is 10 plus negative 8 is 2. And 2 times negative 2 plus 1 is negative 3. 2 times negative 2 is negative 4, plus 1 is negative 3. Does that make sense? Sweep down, kill this 2 off. Negative row 1 added to row 3. Negative 2 plus 2 is 0. That was the point, making zeros there. Negative 1 times 4 is negative 4 plus negative 5 is negative 9. Negative 1 times negative 1 is positive 1 plus negative 4 is negative 3. Negative 1 times 5 is negative 5 minus 8. Negative 5 minus 8. Oh, sorry, wrong one. Negative 1 times 5 is negative 5 plus 1 is negative 4. Sorry, I looked up and down, grabbed the wrong row. Third row is what we're going on. Negative 1 times negative 2 is positive 2 plus 8 is 10. Does that make sense? Now I got to go after this negative 6. 3 times 2 is 6 plus negative 6 is 0. 3 times 4 is 12 plus 0 is 12. 3 times negative 1 is negative 3 plus 7 is 4. 3 times 5 is 15 minus 3 is 12. And 3 times negative 2 is negative 6 plus 1 is negative 5. That was just to get those zeros right there. Does that make sense? Did I lose you guys anywhere? I'm just beginning to do this now. At the same time, let's make L. Now, L is always square. How many rows do we have on this thing? 4. So L is always square, and it's going to be based on the number of rows of the original matrix. So this is going to be a 4 by 4 because there are 4 rows. Does that make sense? L has always got to be square. Now, here's what you do. You remember L had a special look. L always has 1s on the diagonal, you with me? And it's lower triangular, which means above this, you're going to get a bunch of zeros. Does that make sense? This is the goal. This is what L is going to look like. It's going to have 1s on diagonal, and above the 1s, above that diagonal, it's square. It's always going to have a 0. This is called lower triangular. So the lower part's going to have your numbers. And L is the only one that has 1s on the diagonal. So to create this thing, you look at, see this guy right there? That goes with that first column that you played with, that 1. What are the numbers beneath this guy? So you look at the column. So L is all about the columns. Focus on columns. Focus on columns. Okay? Now, you see this was a 2. How do I convert a 2 into a 1? Multiply 1/2 times column 1. Does that make sense? What's half of 2? 1. What's half of negative 4? Negative 2. What's half of 2? 1. What's half of negative 6? Negative 3. And I just got my first column on this thing. Does that make sense? Now, we're going after this guy, okay? Here is the 3. You're going to take this guy. Don't make him a pivot on the U. The pivots will show up on the L. So I'm going to take this and sweep down and make some zeros, right? What am I going to do? I'm going to do, let's see here, 3 times row 2 added to row 3. And I'm going to do negative 4 times row 2 added to row 4. Whatever I add to is what I replace. Okay? So I'm sweeping down. So this top row is going to stay the same. 2, 4, negative 1, 5, negative 2. This was a 0. Now sweep down. Negative 3 times 3 is 3 times 3 is 9 plus negative 9 is 0. That's kind of the point. Well, this row stays the same. I'm jumping down here. 0, 3, 1, 2, negative 3. Now sweep down. 3 times negative 3 is 9 plus negative 9 is 0. That was the point. 0, 0. Okay, and now let's do the rest up. What's 3 times 1 is 3 plus negative 3 is 0. times 2 is 6, plus negative 4. 6 minus 4 is 2. And then 3 times negative 3 is negative 9, plus 10 is a 1. Does that make sense? I swept down by multiplying by negative 3, positive 3 times row 2, adding it to row 3. Now I'm going to do negative 4 times row 2, adding it to row 4. The 0 times 0 is still 0, so let's go after this one. 3 times negative 4 is negative 12, plus 12 is 0. Negative 4 times 1 is negative 4, plus 4 is 0. Negative 4 times 2 is negative 8, plus 12 is, negative 8 plus 12 is how much? 4. And last one, let's see here, negative 4 times negative 3 is a positive 12, and 12 minus 5 plus negative 5 is 7. Does that make sense? All right? So I've got this guy. Now, this was my pivot right there. Do the same thing, but it's upper triangular, so I got this. This first column is going to stay the same. It's 1, negative 2, 1, negative 3, 0, 0, 0, 1. Okay? 0, 0, 1. And there. But now there's that same position right there. I want to make that 3 into a 1. What am I going to do? So this will be the second column just below it. All you care about is the numbers below it. What do I got to do to a 3 to get a 1/3? I screwed that up. What do I got to do to a 3 to get a 1? Multiply by 1/3. So this will be 1/3 times column 2. Does that make sense? Column 2. Only care about is the stuff below it. So a third of 1 is 1. A third of 3 is 1. A third of negative 9 is what? A negative 3. And a third of 12 is equal to 4. So I got that part. I got one more number to figure out before I got my L matrix. So you kind of do these things at the same time. So once you've done this one, you come over here and do this one. Now I got this one, and now I've got to have, where's my next pivot going to be at? Okay, you got it. It's going to be down here. You flip down, my next pivot is going to be this particular 2 right there. You with me? Now, what do I need to do? Because I want to make a 0 below it. I'm going to do what? Negative 2 times row 3, add it to row 4. Just one move. What do I get when I do that? Well, this will be the same. 2, 4, negative 1, 5, negative 2, 0, 3, 1, 2, negative 3, 0, 0, 0, 2, 1. Now I'm going to take this guy and sweep down. 0 times negative 2 plus 0 is a bunch of zeros. Negative 2 times 2 is 4, negative 4, plus 4 is 0. That was the point, making that guy 0. Negative 2 times 1 is negative 2, plus 7 is what? 5. Does that make sense? Now, look at this row right here. This one is a 2. So I want to look at column number 4 down here, where that pivot's located at. Circle your pivot. This will represent it. So how do I turn a 2 into a 1? What do I have to do? 1/2. So I'm going to multiply 1/2 times column. Now which column is this one in? This one's not in column 3, but it's in column 4 is where the pivot's at in terms of column 4, half of column 4. So this stays the same. 1, negative 2, 1, negative 3. This is 0, 1, negative 3, 4. 0, 0, 1. You want this to be a 1, so you multiply by 1/2. You got to do the same thing with this column. 1/2 of 4 is 2. And the last column is always the same. 0, 0, 0, 1. And you just got them. This is the L matrix. And this one here is the U matrix. And you did your LU factorization. And then, of course, always do this. Remember, A is equal to L times U. And I would go back and check. A is equal to L times U. So let's just double check that and make sure I did not screw it up. These are large, so again, we're going to be more calculator proactive on this thing. So here we go. Matrix, edit. Instead of L, I'll call him A. What size matrix is this? 4 by 4, right? What are my numbers? 1, 0, 0, 0, negative 2, 1, 0, 0, 1, negative 3, 1, 0, and then negative 3, 4, 2, 1. This is my L. I'm just going to check it. Matrix A is my L. And that is, did I type it incorrect? That's where I would make a careless error. So yes, I did. Now, let's talk about matrix B. Let's edit matrix B. Matrix B is going to be my U matrix. Okay? What size matrix is this guy? 4 by 5, 4 by 5. And this will be 2, 4, negative 1, 5, negative 2, 0, 3, 1, 2, negative 3, 0, 0, 0, 2, 1, 0, 0, 0, 5. And I double check matrix B is this 2, 0, 0, 4, 3, 0, 0, 1, negative 1, 0, 0, 5, 2, 2. Oops, I made a goof. I did not type it incorrect, did I? It happens to all of us. That's why you check this mess. B, it's down here. 0, 0, 0, 0, 5. There we go. 0, 0, 0. I want this one. That's going to be 5. Okay, check and quit. Call up matrix B again. 2, 0, 0, 4, 3, 0, 0, 1, negative 1, 0, 0, 5, 2, 2, 0, negative 2, negative 3, 1, 5. Yep. Now, what am I going to check? LU. L was A, U was B. LU. Matrix A, L times matrix B, U, LU, and let's see if this thing doesn't pop up. 2, negative 4, 2, negative 6, 4, negative 5, negative 5, 0, negative 1, 3, negative 4, 7, 5, negative 8, 1, negative 3, negative 2, 1, 8, 1. Bingo. I did my LU factorization. But always double check, because if you made a careless error, right there's where it's going to show up at. And again, notice I am using my calculator to double check this thing. I could do it by hand, but once you got it to this level, you got to. But you're going to have to go and remember to do your LU at the same time. So again, notice what I did here. I start with A, and you don't on the U, you don't have the pivots here. You just you got the elements. You're just going to sweep down and make zeros. On the L, you got to have them to be 1. So you turn the pivot here into the 1 over here for the L. U, you sweep down. L, you make pivots. Then once you sweep down and make zeros, then you got this 3 here. You're going to make that going to be a 1. So you multiply by a third on everything below it to get it here. So you're kind of building the L as you're row reducing the U, and you get them at the same time. Does that make sense? It's not difficult. It's incredibly tedious, but it's not difficult. All right. So, because of how awesome this stuff is, all right, let's do one more. Notice the last one, A, was not a square matrix. But on this one, A is a square matrix. It doesn't matter. What size matrix is this guy? 4 by 4. This one is 1, 3, 4, 0, negative 3, negative 6, negative 7, 2, 3, 3, 0, negative 4, 5, negative 3, 2, 9. And I want to do the LU factorization or decomposition, if you will. All right. Here we go. And again, these are my words to understand this stuff. We're going to have to find what U is, and we're going to make L at the same time. All right. So the first thing I'm going to do is let's start with A. Let's recopy. 1, 3, 4, 0, negative 3, negative 6, negative 7, 2, 3, 3, 0, negative 4, and then 5, negative 3, 2, 9. Just recopy the old matrix A here. Okay? Making L, what's so special about L? Well, this guy's square 4x4, so this guy's gonna be also square 4x4, whatever the number of rows is, or what square matrix this is. But you're gonna have ones on the diagonal. Since it's 4x4, it's 1, 0, 0, 0. Right, then it's gonna be, some number 1, 0, 0, then it's gonna be a number 0, and it's gonna be a 1 down here. Down here is what you need to find, but that's gonna be my look of making L out of it. Does that make sense? So here we go. This one is already a pivot, it's kinda nice. I'm gonna sweep down. What kills off a -3? 3 times row 1, just add it to row 2. And whatever I add to is what I replace. Now I'm gonna sweep down and kill this guy off. It's a 3, so I'll multiply by -3 times 1 equals -3 plus row 3, make the 0 there. And then I got a 1 going after a 5. I'm gonna do -5 times row 1, add to row 4. Does that make sense? So let's do that. So the top row stays the same. It's 1, 3, 4, 0. Now 3 times 1 is 3 plus -3 is 0. 3 times 3 is 9 plus -6 is 3. 3 times 4 is 12. 12 minus 7 is 5. 0 times 3 is 0 plus 2 is 2. So I got 0, 3, 5, 2. Let's keep going. Multiply by -3. -3 times 1 is -3 plus 3 is 0. 3 times -3 is -9 plus 3 is what? -6. -3 times 4 is -12 plus 0 is -12. -3 times 0 is 0 plus -4 is -4. Now let's sweep down and get this last guy. -5 times 1 is -5 plus 5 is 0. -5 times 3 is -15. Minus 3 is what? -18. -5 times 4 is -20. Plus 2 is another -18. And -5 times 0 is -5 plus 9 is 9. Does that make sense? Now, I've got him. Now let's take this guy. This guy's already a pivot. You with me? So I don't have to do anything. So this is just going to be column 1. You want that a pivot, and basically you want to make that a 1, but it's already a 1, so you just copy your numbers down. -3, 3, 5. Does that make sense? Now, look at back to your U. Where's your next pivot at? So I'm going to block these guys in, so you can see them. So that's important. Now this 3 is going to be important. With me? And I'm going to sweep down and kill these 2 guys off. So I'm going to multiply, to kill off a 6 from a 3, I'm going to multiply by 2. 2 times row 2, add it to row 3. And kill off an 18, I'm going to multiply by what? 6 times row 2, add it to row 4. Okay? So the top row stays the same. 1, 3, 4, 0. Second row stays the same. 0, 3, 5, 2. Now sweep down. 2 times 3 is 6 plus -6 is 0. So I get 0, 0. 2 times 5 is 10. Minus 12 is -2. And let's see here. 2 times 2 is 4. Plus -4 is 0. Agreed? Now, keep sweeping down. I'm going after 18, multiply by 6. 6 times 0 plus 0 is still 0. 6 times 3 is 18 plus -18 is 0. 6 times 5 is 30. And 30 plus -18. 30 minus 18 is 12. Okay? And then the last one, 6 times 2 is 12, right? Plus 9. 12 plus 9 is 21. Agreed? Now, once we got this, we're going to go back and sweep this guy. This column was the same. 1, -3, 3, 5, 0, 0, 0, 1, 0, 0. Now, this guy, see that 3? We're going to make him into a 1. How do I do that? That I'm going to have to multiply 1/3 times column 2. And only the stuff below it. So a third of 3 is 1. A third of -6 is -2. A third of -18 is a -6. Does that make sense? Okay? building them as I go. Well, this one, all I gotta do is one more move. This is my pivot right here. I'm gonna sweep down and peel off a 12. -2 times what equals -12? 6. So 6 times row 3, add it to row 4. This will be 1, 3, 4, 0, 0, 3, 5, 2, 0, 0. Here we go. 0 times 6 is 0 plus 0 is 0. 0 times 6 is 0 plus 0 is 0. 6 times -2 is -12 plus 12 is 0. That was the point. 6 times 0 is 0 plus 21 is still 20. There's my guy there. And now, right here, row 1 was the same. 1, -3, 3, 5. Row 2 is the same. Column row 1 is the same. Column 2 is 0, 1, -2, -6. Column 3 is going to be 0, 0, 1. Okay. So, what do I need to multiply by? To get rid of a -2 to make it a 1, -1/2 times column 3. So, that makes -1/2 times -2 is 1. -1/2 times 12 is what? -6. And this guy is going to be the same. 0, 0, 0. That's got to be a 1. So that is my definition of the L. And once I got the, it's upper triangular. This guy right here is my U. And then, of course, we're going to verify. Okay? And how do I verify? A has got to be equal to L times U. You just want to double check that. Second matrix, edit, A. These guys are now 4x4s. 1, 0, 0, 0, -3, 1, 0, 0, 3, -2, 1, 0, and then 5, -6, -6, 1. I double check it. I call that matrix A. 1, -3, 3, 5, 0, 1, -2, -6, 0, 0, 1, -6, 0, 0, 0, 1. Yeah, that's good. Now let's do B. Edit B. But this one's now going to be a 4x4. So moving it over here. So I've got 1, 3, 4, 0, 0, 3, 5, 2, 0, 0, -2, 0, 0, 0, 0, 21. Call up my matrix B and double check to make sure I'm happy with what I typed in. Yep, 3, 3, 4, 5, -2, 0, 2, 0, 21. Okay, good. Now, LU would be pretty much A times B. So matrix A times matrix B. LU, L was first, then U was second. And then hit enter. And then I double check myself that 1, 3, 4, 0, -3, 6, -7, 2, 3, 3, 0, -4, 5, -3, 2, 9. I have a winner. And I verified it. Make sure I didn't make a bonehead here. Was there? Yeah.
So, a pattern that I've noticed is that every number that we're multiplying, whatever we're multiplying everything by
Yeah.
is what we put into the,
You're talking about in terms of making L?
yeah.
Yes, that's exactly right. So this one was a 1, so you can recopy it. Now this one was a, but you see, you had to row reduce it, so you had to go after this guy. Now it's a 3, because you got to make your zeros first, then you multiply that times a third on everybody below it. Then you take this guy and sweep down here, now that's a -2, so anybody below him gets multiplied by -1/2. There's a pattern there, yes ma'am.
Right, but, so could we just, cause like a 3, -3, -5 that we used to reduce that was just placed in the other matrix, just with a different opposite sign. Is that a pattern that we can kind of rely on to make out?
No. What are you talking about? Okay.
So we multiplied U, like each row in U by 3, -3, -5 below.
Yes.
And then we used those three numbers to put into L, just opposite same thing with one below, 2 and 6, we just put into L.
Okay,
-2,
so
-6.
this was a 3, this was a -3, you just use the opposite sign. And then you went, here was a 3, so what do we do here? 2, -2, and -6. And then over here, which is a 6, where did that show up? It showed up down here as a -6. I never paid attention to that. Let's go back, wait. Let's see if it worked on the last one. It does? Then you could probably go with that. Yes, let's see here. This one was the one we did before this. This one was a 2, we swept down here, and this was 2, -1, 3. So you made that a point. -2, +1, -3, there you go. This one here was a 1, so you made him. So you had to sweep down 3, -4. Opposite signs of that would be, that is -3, 4, so that's good. And then here was a -2, so that should be a 2 down here. It is. Yes, there's a pattern. Go and discover these things. So yes, I never really actually paid attention to it. It's actually these numbers over here, but yes, you are correct. It is exactly what's going on.
And you needed a theorem to get a doctorate degree, right?
Yes, you do. And I'm sure that being this is a 2,000 level class, that somebody's already come up with that theorem, but I never actually read it, so done it. So, all right. But yes, you do have to come up with a new theorem that no one else has discovered. And so, but you're on your way. There we go. So, all right. Next section is section 2.6. The Leontief input-output model. So let me start you over here with this. This is basically a model of how to actually solve a word problem of a special type. And usually these are economic problems and stuff. So the Leontief input-output model is an economic model that has, quote, M parts. You know, and you're going to be some kind of production, whether it's cars, clothes, whatever. This is a production of word problems. So we got another whole section of doing word problems, but it's a special type of economic problem. So you're going to see the formula in just a second, but here's the deal. So the Leontief input-output model is an economic model where you have n parts. So you are going to get some kind of interesting square stuff out of this with these n parts. X vector is the production vector in Rn. For those n parts, this is Rn. This gives the output of each part of the economy. Typically, we do this for 1 year. So we're going to be looking at it, again, this is an economics problem, looking at it from a 1 year perspective, and you've got n parts of this thing. You know, agriculture, what are some other ones I put in there? Agriculture, mechanics, service, manufacturing, some kind of output that you have that you're going to be analyzing and stuff. All right. So this gives that. So the X factor is going to give you the output of each of the part of the economy that you're analyzing. The agricultural part, the manufacturing part, the service part of whatever you're identifying your economics is. You're also going to have something called a D vector, which is called the final demand vector. This lists the values of the goods and services demanded by the non-producing part of the economy, i.e. people not working on cars that want them, you know, consisting of consumer demand, okay? So, and don't be, you know, discouraged by this non-producing part of the economy. We're looking at agriculture, we're looking at service, we're looking at, let's see here, agriculture, service, manufacturing, something like that. So if you're not working in manufacturing, you're not working in the farming industry, and you're not in the service industry, you are, quote unquote, the non-producing part of the economy. You're producing something else, but not what we're analyzing. Does that make sense? And so, but you want to buy what we're interested in, a car, or some other type of manufacturing good or something like that. So because, you know, that's who you're going to sell it to. So that's what we mean by this non-working people that are not working, not in this industry. But you are going to create the demand for my industry, and this is what's going to create the capitalism of trying to sell you something or other for a particular price and what those prices need to be. So Intermediate demand is by definition, again, this is word problem, so here we go. The intermediate demand is what the producer needs in order to make their product. Okay, so we have the demand, this big D final demand, that's listed by the people who are going to sell, purchase, excuse me. They're going to purchase what I'm selling. And we have this intermediate demand, which is what the producer needs in order to make the product. So we need agriculture. We're going to need some manufacturing, and we need some part of that service to create whatever object that I want to create in this thing here. This is the formula for this. This is where the Leontief input-output model comes from. The amount that is produced, X, will be equal to the intermediate demand plus the final demand. Here comes the idea here. The amount that I'm going to be producing is the intermediate demand, what it takes to produce this stuff, plus the final demand, which is what we're going to be wanting to sell this stuff to and for. Okay? So your Leontief problem, this is what you need. Always go for math formula with these level classes, is this. The Leontief input-output model is this. X, which is the amount produced, is equal to C times X. This is the consumption matrix. Now look at this consumption matrix. What is my consumption? Now, we know what we need. Remember, this is part of that intermediate demand, which is what the producer needs to make what the producer needs in order to make the product. So we got this consumption, what stuff we're actually using times that same demand here, okay? The amount that we need to produce. So the amount that we need to produce times how much we're going to be consuming, plus that final demand, which is set in the economics of the industry or whatever I'm trying to produce, okay? So this consumption matrix right here, you're going to see this in an example in just a second, but this is going to be based upon those services. Let's say agriculture, the service industry, and the manufacturing industry that creates the stuff that I need, that I put together to create the product that I want to sell. So we have this consumption matrix based upon what we need, times the X, which is the amount I'm going to be producing, plus that demand will be equal to the total amount I'm producing. So, I got a question for you. So this is the Leontief input-output model, okay? I want you to solve for X. So I took the equation right here. So this is the Leontief input-output model. I want you to solve this thing for X. How would you do that? Let's do the math. Well, if I'm going to solve something or other, for any variable, I like to get everybody with that variable on one side of my equation. So my first move is I'm going to subtract C times X. When I do, it'll cancel here. Again, this was your famous Leontief input-output model. I'm going to subtract CX, and that's going to give me X minus consumption matrix times X is equal to that final demand vector. Does that make sense? Now, this is important. You're going to see this again. I want to solve for X. I got X in two terms. I would like to factor it out, but I got a problem here. This is a vector, right? This is a matrix times a vector. So you give me another vector. But to be able to factor this stuff out, I got to be able to like terms. So here's what I'm going to do. What does I stand for in the wonderful world of linear algebra? Not inverse. What is it? Identity. The identity. So 1's on the diagonal, 0's off the diagonal. Okay? I can replace X with I times X minus C times X equals D. This is a very important move because the only way you can factor stuff out doing algebra is you got to have like terms. So the first guy doesn't have a matrix times it. The second guy does, and I want to be able to factor out that X. So I got to rewrite just that vector by himself as a matrix times a vector. Well, just the identity times the vector will give me back to the vector back again. So this was a classic trick. Now notice this. You've got X in this problem. Now you've got matrix times X minus matrix times X. You know from our properties of matrices, we can factor out X, but X is in the back. Important. Order matters. So this gives me identity minus C times X, I factored it in the back, is equal to the demand vector. Now, how would I solve for X? Well, I got this I identity minus C times X equals D. Well, this is a big matrix, right? So I'm going to multiply by I minus C inverse on both sides. But notice the big matrix is on the left, So I gotta multiply I minus C inverse onto that. And what I do to one side, I have to do the other on the left. This will cancel, the inverse times a matrix, you get the identity out of it. So this will give you the identity times X is equal to the identity minus C inverse times D. Identity times X is just X. X is equal to, you take I minus C inverse, multiply it times the D vector, and that's going to give you your solution. This is how you quote unquote solve for X out of this guy. Again, the trick though was right here. This was the trick to be able to show the math and how to solve for X. You multiply any kind of vector, you want it to be more of a matrix representation times it because it's got to look like the other guy before you can start factoring out. So any vector you multiply times the identity times the vector, and now it's got the same format of matrix times vector, so you can factor out the vector, and there's the matrix, and you do the inverse of that matrix on the other side. So, with this, and with the Leontief input-output problem here, let us look at a example. I stole this one out of the textbook, because where else you would come across a problem like this one. But so, here we go. Give you a chance to write this one down, but here it is. Now, what you need for the Leontief input-output model is you gotta have two things. You need to have the demand, and you need to have the consumption matrix. We're gonna give you those things, but look at how they're given, okay? Consumption matrix. You're gonna be given some data, so rewrite the data as a matrix. All the numbers must be in decimal form. Typically they talk about the percentage. So you know it's gonna be a fraction of the total. So the most you can ever get is a 1, which would represent 100%. So you're expecting decimals on this thing. So I want my decimals is what I'm telling you right here. So input consumption per unit output. This is what we got here, okay? Inputs consumed per unit of output. So manufacturing uses 50% or 0.5 of its own manufacturing. Manufacturing uses 0.4 or 40% of the agriculture, and manufacturing uses 20% of the service that's being provided. So to be able to create the manufacturing, it comes from manufacturing. 50% of it comes from manufacturing, 40% comes from agriculture, and 20% comes from service. The agriculture, to create the agricultural consumed, it takes 20% of what's being manufactured, 30% of the agriculture being being consumed there, and 10% of service. That's what gives you the agricultural aspect. The last one is service. So for services, you use 10% of what's being manufactured, 10% of the agriculture, and you use 30% of the service to create more service out of this guy. So these are your kind of your variables here: manufacturing, agriculture, and service. I call that C1, C2, C3. Okay? So in other words, if you look at the manufacturing, this top line up here, so manufacturing needs. The needs for the manufacturing is 50% from the manufacturing. You've got to actually use the stuff you're manufacturing to be put into what you need for manufacturing. 0.4 or 40% of the manufacturing needs agriculture from the agricultural industry, and 20% comes from service. 0.2, 20% comes from services. And this particular matrix, the way it's designed, is your consumption needs and stuff, consumption matrix, and it's pretty much, you just turn this into a big old block matrix here, and you'll see that where I got my matrix is going to be right across the row. 0.5, 0.4, 0.2, 0.2, 0.3, 0.1, 0.1, 0.1, 0.3. There's my consumed matrix here, okay? So, make sure you get that thing down. So I had to give you the example. Here comes my example down here. All right. Based upon what I gave you, and all that stuff I gave you is what I would give you on a test or any kind of question it is. Okay? So here it is. Suppose we have the same economic as before, and I just mentioned it to you, and if the final demand is 50% units of manufacturing, 30% or 30 units of agriculture and 20 units of service. So you got 50 units of manufacturing, 30 units of agriculture, and 20 units of service. Find the production level X that needs to satisfy this demand. So we're going to give you the demand equation. So what is my demand? My demand is, in terms of units, 50% of the units I produce have to come from manufacturing, 30 units have to come from agriculture, and 20 units come from service. Remember this was my C, or my consumption matrix. That was at 0.5, 0.4, 0.2, 0.2, 0.3, 0.1, and 0.1, 0.1, and 0.3. So, remember what you got here is this. Remember, X is equal to C times X plus D. Right? How are you going to solve for X? We just solved this equation just a few seconds ago. Let's do it again. So, I would do I times X equals CX plus D, just multiplying by dividend, kind of gives me like terms. And then I want to subtract CX from both sides. And that gives me I times X minus CX equals D. Got the D demand vector by itself. I can factor out the X in the back, so I've got I minus C times X equals D. And what's going to kill off that I minus C? X is going to be equal to I minus C. What do? Inverse to put him on the other side times D. Does that make sense? So, to solve for X, I'm going to have this. Okay, in terms of this equation right here, based upon these two concepts. What size matrix is this guy right here? It's got to be square. Always square with these consumption matrices. What size is it? 3 by 3. So this identity is going to have to be 3 by 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. Minus C. C was given to me. This is your identity. C was 0.5, 0.4, 0.2, 0.2, 0.3, 0.1, 0.1, 0.1, 0.3, times the X vector is equal to the D vector, and the D vector was this 50, 30, 20. Does that make sense? Did I lose you anywhere? All right. Now, what exactly would this be? In terms of matrix, what's 1 minus 0.5? That isn't 0.5. I have to read my handwriting here. What's that? 1 minus 0.5 is 0.5. What 0 minus 0.4 is a negative 0.4? What 0 minus 0.2 is a negative 0.2? 0 minus negative 0.2 is a negative 0.2. 1 minus 0.3 is a 0.7. 0 minus a 0.1 is a negative 0.1. 0 minus a 0.1 is a negative 0.1. 0 minus a 0.1 is a negative 0.1. And 1 minus a 0.3 is a 0.7 again. You'll notice on your matrices, the main diagonal ends up being positive, but the off diagonal, upper and lower, are going to end up being negative because of that 1 minus. And all these numbers in here have to be percentages or decimals, so most it's ever going to be is going to be a 1. So the rest of these guys are going to have to be numbers. Multiplied times X is equal to the 50, 30, 20. So to solve for X, you take 0.5, 0.4, negative 0.5, negative 0.4, negative 0.2, negative 0.2, 0.7, negative 0.1, negative 0.1, negative 0.1, and a 0.7. Inverse of this guy, times 50, 30, 20. Okay? And if you do that, you'll end up getting this. And again, I'm skipping some steps because honestly, with this kind of inverse, I would do it on the calculator. I got 225.9259259. I get 118.5185185, and I get 77.77778. Now, remember that matrix? They were done in order. So this is just inverse times this guy. This was manufacturing, this was agriculture, this was services. This is going to be manufacturing, agriculture, and services. So my equilibrium, where I gotta set my demand for in terms of what I need to produce the demand that's out there, I need 225.9 units of manufacturing, 118 units of agriculture, and 77.7 units of services to be able to satisfy the demand that was given to me about this. 50 manufacturing, 30 units of agriculture, and 20 units of services and stuff. Now, a couple of things. Notice, one, you see these guys right here? They should all be what kind of numbers? Positive. This is the demand for how much you need or how much you want to produce. You cannot produce negative stuff. So anytime you've got a problem where you've got a bunch of negatives on this thing, it can't be solved. It cannot be done. You're expecting all the solutions of this thing to be positive to actually find this point where you need to do your production. If any one of these guys is negative, that means I've got to recreate something or other out of it. You can't do that. So you can't have negatives on these guys. These answers should always be positive to actually validate the solution stuff. We'll study more on this one, but this is your Leontief input-output model. I'll see you guys next time.
So when you're getting that final answer, just from the last step, or from the, from there to the last step, you just put that in your calculator?
I did.
Okay, that's what I was just making sure.
I went matrix, let me show you. Edit A, what size is this guy? Well, first off, it was this one right here.
Yeah.
Right? So this thing is 3 by 3. I'll show you 3 by 3. Oh, not 33, 3 by 3. I just typed this in. 0.5, negative 0.4, negative 0.2, negative 0.2, positive 0.7, negative 0.1, negative 0.1, negative 0.1, 0.7. Right?
Yep.
That was matrix A. And I just make sure I got the right numbers here. I do. All right. And then under B, I need to put that vector in there. B is going to be my demand that I needed. Here, this one is a 3 by 1, right?
Yep.
So this was 50, 30, 20. Okay? And then I'm just going to do A, matrix A, inverse. Remember the inverse button there? It's a little -1 there. Times matrix B. And notice where I got my number.
There we go.
Yeah. And I'm doing the quick way on the calculator because, okay, row reducing this crap to find the inverse. It's painful. You know how to do it, but at some point we're going to be using the calculator, especially with these modeling